Imagine holding a digital paintbrush, right? But this brush actually remembers, like the nervous tremor in your hand from a painting you did maybe 3 years ago.
Oh, wow. Yeah.
You make a stroke on the canvas today, and the brush subtly adjusts its pressure, its texture, completely anticipating your specific idiosyncratic style.
That's wild.
It knows you, and better yet, it is a piece of software that you own entirely. Like it's living on your hard drive, completely severed from the internet
Yeah.
with 0 monthly subscriptions.
And no corporate server monitoring what you create, right?
Exactly.
I mean, it sounds like pure science fiction. We are so conditioned to think of tools as just, inert objects, or
Yeah.
at best, rented software that just resets the second we close the browser.
Yeah, you log out and it forgets you.
Exactly. But mathematically distilling human artistic identity into an offline, self-contained file is not a hypothetical future. It is literally happening right now on consumer-grade gaming computers.
Right. And today we are taking a massive deep dive into a very specific, almost rebellious corner of the creative tech world. We're unpacking this incredibly dense technical paper called Arynwood Digital Hybridization.pdf.
Yeah, fascinating document.
It really is. It documents the research of an artist and developer named Lorelei Noble. She successfully trained a sophisticated AI model, specifically a low-rank adaptation, or LoRAi, on the SDXL architecture using nothing but her own human artwork.
Right, which is huge.
And alongside that paper, we are tearing into the system documentation for the software environment she actually built to do this, which is called the ArynCore MCP.
The multi-context platform, yeah.
So if you were listening to this on a commute or, sitting at your desk, just think about the hundreds of hours you might have poured into a hobby, like painting or writing or playing guitar.
Oh, for sure.
Now imagine feeding all of that into a localized machine to basically create a digital ghost of your own creative process.
And the key word there is localized. I mean, the
Yeah.
entire philosophy driving Arynwood Technology is self-sovereignty, because the industry standard right now is to rely on massive, multi-billion-dollar cloud infrastructure. You pay a subscription, you type a prompt into a web portal, and, a server in another country processes the math and sends you an image back.
Yeah.
Lorelei Noble's research is all about severing that umbilical cord.
But I want to play devil's advocate for the corporate cloud for a second here.
Okay, go for it.
Because we shouldn't pretend it doesn't have massive benefits, right?
Yeah.
If I use a giant corporate AI service, I am getting guaranteed uptime. I'm getting safety rails.
Bruh.
I don't have to worry about my computer crashing or my graphics card like catching fire
Yeah.
because I pushed it too hard.
Yeah, the hardware burden is on them.
Exactly. So by moving all of this complex machine learning to an off-grid, localized setup, aren't we just taking on a massive, unnecessary IT burden?
Well, the safety net of the cloud is undeniably convenient, yeah. You completely outsource the computing power and the maintenance. But the Arynwood counterargument is really about the cost of that convenience.
Which is what...
Ownership and privacy. When you rent access to a cloud model, the corporation can change the model overnight.
Oh, right. They update it and suddenly your prompts don't work.
Exactly. They alter the terms of service.
Yeah.
They can decide your specific art style violates a new internal policy, and suddenly the tool you rely on is just gone.
Wow, yeah. That's terrifying for a working artist.
It is. So the ArynCore MCP is built on the premise that true creative freedom requires owning the literal infrastructure of your workshop.
So let's actually look at the blueprints of this workshop, because the documentation describes ArynCore as a local desktop hub. But looking at the feature list, it seems more like a heavily fortified bunker.
It's massive, yeah.
It has a chat interface connecting to local language models, a project tracker called Redmine, personal finance ledgers, an IMP mail client, and just this absolute arsenal of GPU-heavy audio and video tools.
Right?
To me, throwing all of that into one desktop app sounds like a recipe for a frozen computer. How does the architecture prevent my machine from grinding to a halt the second I open it?
That is the core engineering challenge of local AI, right there. If you try to run all those models simultaneously, a standard consumer PC will absolutely choke.
Right.
So the ArynCore backend solves this using what they call sidecars. It's a completely modular approach. The main application is built using Python, specifically utilizing a framework called FastAPI and a database structure called IOSlate.
Wait, stop right there, because those are two terms that get thrown around a lot in developer circles, but I want to clarify them for the listener.
Sure.
I know what an API is. It's how software talks to other software. But what makes FastAPI special in this context?
It comes down to asynchronous routing. So think of a traditional web server, like a restaurant with only one waiter.
Okay.
If a customer orders a highly complex meal, like rendering a massive video file, that waiter has to stand in the kitchen and literally wait for the food to finish cooking before they can serve the next table.
Oh, so everything just bottlenecks.
Exactly. Fast Apply, though, is designed for asynchronous operations. It's like having a system where the waiter places the complex order with the kitchen and immediately goes back out to take orders from 20 other tables.
Okay, that makes sense.
Right. And when the kitchen finishes the heavy job, they ring a bell and the waiter grabs it.
Okay, so the UI remains completely responsive even if your computer's graphics card is in the basement, sweating over some multi-gigabyte machine learning task.
Precisely. And that ties into ISGlide, which is really simply a way for the database to handle information asynchronously as well.
Got it.
And the front end, what you actually click on, is built in React 19 and bundled using a Tori desktop launcher.
Yeah, I noticed that detail in the RiaDB. Why Tori? Why not just make it a web page or use something like Electron? Because Electron powers a lot of desktop apps like Discord or Slack, right?
It does, but Electron is notorious for being incredibly resource heavy.
Really?
Yeah, it essentially packages an entire Chromium web browser into the app, which eats up a ton of RAM just to sit idle.
Oh, wow. Just to be open.
Right. Tori, on the other hand, hooks into the operating system's native web rendering engine, so it is incredibly lightweight.
I see.
When you're building a tool specifically designed to run massive VRAM-hungry AI models locally, every megabyte of system RAM you save on the user interface is a megabyte you can reallocate to the actual creative generation.
That makes total sense. You want the canvas to be as light as possible so the paint can be as heavy as it needs to be.
Exactly.
And the system actually watches that weight in real time. Right? The dashboard uses something called Prometheus and a tool called NVIDIA Smeets to actively monitor your graphics card's VRAM.
Yes.
It puts a live readout right on the home screen.
Because transparency is critical here. VRAM, or video RAM, is the absolute lifeblood of local AI.
Oh, right, because it's different from regular RAM.
Completely. Unlike normal system RAM, which handles general computing tasks, VRAM is located directly on your graphics card. It's optimized for the massive parallel mathematical calculations required by neural networks. If you exceed your VRAM limit, the generation doesn't just slow down, it completely fails. ArynCore forces the user to see their hardware limitations up front so they don't crash their system.
But let's go back to your sidecar analogy, because that explains how it manages the heavy lifting. How does the sidecar actually function within this asynchronous restaurant we just built?
A sidecar is basically an entirely isolated process running on a different network port within your computer.
Okay.
Let's say you want to use the Demux audio separation tool, which I know we'll dive into later.
Oh, definitely.
That specific tool lives in a sidecar on port 804. Now, when you launch ArynCore, port 804 is completely dormant.
So it's not using any juice.
Zero processing power. It's only when you specifically click the separate audio button that the fast API router sends a wake-up call to port 804, spins up the PyTorch environment, executes the math, and then shuts it right back down.
So a completely modular on-demand factory. That is really the only way a single human on a gaming PC can wield an entire IT department's worth of tools. Which brings us to the actual creative application of this factory. We need to transition from the architecture of the workshop to the actual artifact being forged inside it.
Yes, the hybridization project.
Exactly. Let's look at Lorelei Noble's digital hybridization project.
This is a fascinating case study in blending human intent with machine learning geometry. The paper outlines the dual nature of the Arynwood Artifact.
Okay.
And the starting point has absolutely nothing to do with code. It begins with 48 distinct digital drawings created manually in an iPad application called Procreate.
And we are talking about years of work here. Hundreds of hours of an artist physically dragging an Apple Pencil across a glass screen.
Building layers, making mistakes, yeah.
Developing a very specific style characterized by pastel colors and intentional mutations.
That is the human half of the artifact. The machine half is the process of translating those 48 images into a format that a neural network can actually understand.
Right.
Specifically, they're using these images to fine-tune a massive pre-existing AI model using a technique called low-rank adaptation, or LoRAs.
Let's pause and really cement what a LoRA is for the listener, because it's a term that dominates the AI art space right now.
It really does.
If I understand correctly, training a foundational model, like the base SDXL model, takes supercomputers running for months, looking at billions of images.
Yes.
A normal person cannot do that. So LoRa is basically a shortcut.
It is an incredibly elegant mathematical shortcut. Think of the base SDXL model as a chef who has gone to culinary school for 20 years.
Okay.
They know how to cook every conceivable dish on Earth, but their knowledge is generalized.
Right.
If you want the chef to learn your grandmother's highly specific secret marinara sauce recipe, you don't send the chef back to culinary school for another 20 years.
That would be crazy.
You just hand them a small, lightweight index card with the new recipe. They slip that index card into their massive cookbook. The LoRa is the index card.
I love that. It's
Yes.
a tiny file, usually just a few hundred megabytes, that sits on top of the massive gigabyte foundational model, gently steering its generalized knowledge toward your specific style. But how do we get those 48 Procreate sketches onto that index card? Because the source material breaks this down into an intensely manual, 3-stage data set preparation pipeline.
Yeah. Stage 1 is collection, just gathering the highest quality exports of those 48 drawings.
Easy enough.
But you can't just hand an AI model a folder of JPEGs and expect it to learn. A neural network doesn't possess human intuition. It doesn't look at a picture and organically feel the vibe, you know?
Right.
It requires explicit textual metadata mapped to the visual data.
Which kicks off stage 2, the auto-captioning engine. The documentation says ArynCore uses something called WD14 to do an automated pass over the images. What is WD14 actually doing when it looks at an image?
So WD14 is a vision model trained to identify literal subjects and common descriptors.
Okay.
It sweeps its mathematical eye over one of Lorelei's sketches and generates a string of baseline tags. So it might output something like, one girl, solo, looking at viewer, blue hair, muted colors, abstract background.
But there's a massive flaw in relying solely on that, right?
Yeah.
The machine is fundamentally literal. It sees the what, but it is completely blind to the how.
That is the crucial distinction. If you proceed to train the AI using only the tags generated by WD14, the AI will just learn how to generate a generic girl with blue hair against a generic abstract background.
It misses the magic.
Completely. It will ignore the style of the original artwork because the style wasn't explicitly isolated in the text.
And this leads to stage 3, which is where the human creator has to really roll up their sleeves and dive back in. Manual correction.
Yeah, it's tedious but necessary.
The artist has to go through the data set and structure those tags.
Oh,
And the most important part of this stage is mapping everything to a single trigger word. In Lorelei's case, she used the word Arynwood.
yes.
Let's expand on the chef analogy from earlier.
Yes.
It's like taking the master chef of your grandmother's marinara sauce.
Okay.
The automated WD14 system tastes it and writes down tomato, garlic, salt, heat. If the chef cooks that, it just tastes like generic pasta sauce. So the human has to step in, erase those generic tags, and write Arynwood-style sauce.
Exactly.
You force the machine to associate all the subtle, complex, unnameable magic of the sauce with that single new vocabulary word.
That is the exact mechanism of dataset tagging for style capture. By cleaning up the captions and injecting the word Arynwood into every single text file associated with those 48 images, Lorelei is commanding the neural network to isolate the overarching visual technique.
Wow.
She is essentially telling the math, do not focus on the fact that this is a drawing of a train or a face or a landscape. Focus on the brush strokes, focus on the pastel blending. All of those stylistic traits are now defined by the word Arynwood.
So when the training is complete, the user can just type, a photograph of an astronaut on the moon, the style of Arynwood, and the AI applies that captured stylistic DNA to a totally new subject.
Yes. The resulting safe tensors file, which is the compiled LoRa artifact, is literally a mathematical encapsulation of the artist's technique.
But creating that safe tensors file requires actually running the training process, which historically is what melts people's computers.
Oh yeah, it's intense.
I want to look closely at section 3 of our outline, the mechanics of homebrew LoRa training. The paper gives us the exact script executed by the ArynCore backend, SDXL train-network.py, running through an integration with Koya SS.
Right.
So let's assume you're listening to this and you have a decent gaming PC with a good NVIDIA graphics card. You have your 48 images perfectly tagged. When you hit start training, what dials and knobs are actually being turned?
A lot of them.
The documentation lists a bunch of parameters, and frankly, it looks like a cockpit. Let's break them down. First up, we have the network dimension, or the DIM, she's set this to 32. Is 32 a high number?
Well, in the context of SDXL, 32 is a very deliberate, moderate choice. The network dimension dictates the mathematical capacity of the LoRA.
Okay.
If the LoRA is a notebook where the AI is writing down its observations about your art style, the dim is the number of pages in the notebook.
So if you set the dim to 4, it only has 4 pages. It might learn basic colors, but it won't have enough space to remember the intricate details of how you draw eyes or hands.
Correct. You would get an undertrained, really muddy result. But the instinct for a lot of beginners is to just max it out. They think, oh, I want perfect quality. I'll set the dim to 256 or 512.
Giving the AI a massive encyclopedia to write in, why is that bad?
Because of 2 things. First, computational overhead. A dim of 256 will just devour your VRAM and take exponentially longer to train.
Yeah.
Second, and more importantly, it leads to a phenomenon called severe overfitting.
Overfitting.
Yeah. If the notebook is too big, the AI doesn't learn the general concept of your style. Instead, it uses all that extra space to rigidly memorize the exact pixels of your 48 training images.
Oh, I see. So if you ask for an astronaut in your style, but your training data only contain pictures of fantasy castles, an overfitted model will just panic. It
Exactly.
doesn't know how to extrapolate. It'll just try to morph the astronaut into one of the castles it memorized.
Right, loses its imagination entirely. A dim of 32 provides just enough capacity to capture the complex pastel mutations of the Arynwood style, while forcing the model to generalize enough that it can apply that style to completely novel prompts.
Okay, next parameter. Network alpha. You set this to 16. What is alpha?
Alpha is the scaling factor for the weight adjustments. If dim is the number of pages in the notebook, think of alpha as how hard the AI presses the pen into the paper.
Oh, that's a good way to picture it.
Yeah, it determines the magnitude of the changes applied to the base model. Setting alpha to exactly half of the dim, so 16 to 32, is a widely accepted standard in the open source community to ensure the math stays stable.
Next, the resolution is locked at 24 by 2024 pixels. I assume this is non-negotiable because the SDXL base model was originally trained on 124 images, so you basically have to speak its native language.
You must align with the architectural grid of the foundation, yeah? If you try to feed 512 pixel images into an SDXL training run without upscaling them first, the latent space geometry gets totally confused.
All right, then we have the learning rate set to 1E4. That looks like scientific notation.
It is. It translates to 0.00001.
Okay.
The learning rate is basically the step size the AI takes when trying to find the optimal mathematical representation of your style.
Help me visualize that.
Imagine you are blindfolded, standing on the side of a mountain, and your goal is to find the absolute lowest point in the valley. The learning rate is the size of the steps you take.
Okay, I'm with you.
If your learning rate is too high, say you're taking giant leaps, you may completely jump over the lowest point and end up on the other side of the valley. The math becomes unstable.
And if the learning rate is too low, you are taking millimeter-sized shuffles. You'll eventually find the bottom, but it will take you 10 years.
Exactly. So a learning rate of 1E4 is really the sweet spot for LaRO training. It allows the model to descend smoothly into the optimal mathematical valley without wildly overcorrecting or, wasting time.
Which brings us to the final major parameter, epochs. She set the total training cycles to 10, meaning the machine looked at the data set of 48 images, updated its math, and then repeated that entire process 9 more times.
Correct.
Now, I understand the danger of the massive notebook from earlier, the DIM, but if you have a perfectly sized 32-page notebook, why not just read through the data set 100 times? Why stop at 10 epochs? Surely more repetition just cements the knowledge better.
It is the exact same trap as the high dim setting, just approached from a different angle.
Really?
Yeah, overfitting is a function of both capacity and exposure. If you run 100 epochs, you are relentlessly hammering those 48 images into the neural network's weights. The AI eventually gives up on learning the overarching rules of your style and simply resorts to memorizing the answers to the test.
It's like a student who memorizes a practice exam but completely fails the real test because they didn't actually learn the underlying formulas.
That's exactly it.
So stopping at exactly 10 epochs is an exercise in restraint. You pull the cake out of the oven the exact second it's baked before it burns.
It is an art form in itself. The paper emphasizes that tuning the hyperparameters to capture the vibe without destroying the model's flexibility requires immense trial and error.
So after this delicate, computationally heavy process, your computer spits out a completed safe tensors file. You now own a mathematical distillation of your life's work.
Which is pretty profound.
It is. And the next logical question is, where can you take it? And this leads us to what I found to be the most surprising revelation in the research paper. Section 4, Ecosystem Portability.
Ah, yes, the portability finding.
The paper notes that the Arynwood LoRa was trained locally using a base model called Juggernaut XL. From my understanding of the AI community, Juggernaut is a highly photorealistic, beautifully tuned derivative of the original SDXL.
That's right.
And when they applied the LoRa to Juggernaut, it worked perfectly. It captured the pastel mutations with high fidelity.
Which is expected, right? Juggernaut was its native environment. It was the soil in which the mathematical seed was planted.
But then, the researcher did an experiment. They took that same exact LoRa file and dropped it onto a completely different base model called DreamShaper XL Turbo.
Yep.
And they didn't retrain it. They didn't run the SDXL train network.py script again. They just drag and drop the file. And it worked.
This is a monumental finding for localized workflows. To understand why, you have to realize how structurally different those two base models actually are.
Okay, tell me.
DreamShaper XL Turbo is a highly stylized model. It leans heavily toward digital art and 3D rendering, but more importantly, it is a turbo model, meaning its internal architecture has been distilled to require far fewer processing steps to generate an image.
Wow.
So it is fundamentally different under the hood than Juggernaut.
Yet the research study confirmed seamless cross-checkpoint portability. On DreamShaper, the generated images were a bit fuzzier, leaning more into a dreamy artistic output compared to the sharp fidelity of Juggernaut, but the core stylistic identity, the Arynwood trigger, was undeniably present and intact.
Yes.
Let me test an analogy on you. Tell me if this holds up.
Let's hear it.
It's like writing a complex, physics-heavy video game optimized specifically for the hardware of a PlayStation. But then you discover that you can just take the disc, pop it into an Xbox, and it magically runs.
Yeah.
The Xbox might render the lighting a little differently. Maybe the shadows are softer, the colors pop more. But the core game code, the physics, the identity of the game transfers flawlessly without you having to recompile a single line of code.
That analogy perfectly captures the architectural flexibility of the SDXL ecosystem. And from a practical standpoint, think about what this means for a user on consumer hardware.
Right.
We just spent 20 minutes discussing how fragile and computationally expensive the training process is. Even on a top-tier NVIDIA card, training takes significant VRAM, electricity, and time.
You don't want to do that every day.
Exactly. If an artifact is portable across the entire family of SDXL derivatives, you only have to pay that compute toll once.
That is massive.
It is. You invest the hours to train the safe tensors file one time, but once you hold that file, you suddenly have access to an infinite variety of baseline aesthetic environments.
So you can apply your custom style to an anime-focused model, an architecture-focused model, a hyper-realistic photography model.
Yep. The utility of your initial effort is exponentially multiplied.
It is incredibly liberating. But the paper also drops a massive warning sign here. This portability is not infinite. You cannot just take your digital paintbrush anywhere. There's a hard wall, and the research labeled it the SD 1.5 architectural barrier.
Right. We've been operating entirely within the SDXL universe up to this point. But what happens if a user tries to apply their newly minted SDXL-trained Arynwood LoRa onto an older legacy model?
Stable Diffusion 1.5 is arguably the most famous legacy checkpoint, right? This is the model that really kicked off the open source AI art boom.
It was.
And the paper documents the phenomenon quite bluntly. Total failure.
Complete failure.
When the Arynwood LoRa was injected into an SD 1.5 pipeline, the generation completely reverted to the generic baseline of the old model. The Arynwood style tags were completely ignored. The artifact exerted zero influence over the output.
Yeah, it just does nothing.
I want to understand the exact mechanics of this failure. You can't just say they are different versions. What physically breaks down in the math? The paper cites tensor incompatibility. What is a tensor and why won't they talk to each other?
So to understand tensors, we have to look at how an AI organizes information. Imagine a tensor as the physical geometric scaffolding of the neural network's brain.
Okay, geometric scaffolding.
SDXL, being the modern massive architecture, operates natively at a resolution of 1024 by 1024. But more than just image size, it has a vastly expanded parameter count. Furthermore, it uses a dual text encoder system to process human language.
Meaning it reads prompts twice.
It reads prompts using two separate neural pathways simultaneously to grasp deep nuance.
So its brain is incredibly dense, multi-layered, and highly dimensional.
Exactly. The LoRa trained on SDXL is mathematically shaped to fit perfectly into that specific complex scaffolding.
Right.
Now look at the legacy SD 1.5 model. It was designed for 512 by 512 pixel images. It uses a much simpler, constrained, single text encoder architecture. The dimensionality of its brain is fundamentally smaller.
I see. So if we go back to the idea of dimensions, it's like trying to fold a highly complex three-dimensional origami crane using only a one-dimensional piece of string.
That's a great visual.
The structural geometry required by the SDXL LoRa physically cannot map onto the flat, constrained space of SD 1.5.
That is the exact mathematical reality. If the software actually attempted to force the SDXL tensors into the SD 1.5 architecture, the matrix multiplication would collapse.
It would just error out.
The entire generation process would instantly crash and throw an error code.
So the system isn't breaking, it's actually saving itself. It recognizes the incompatible geometry, silently drops the LoRa weights entirely, and just runs the base model to prevent a fatal crash.
Precisely.
It's a stark reminder that while AI generation feels like literal magic, when you type a prompt and a beautiful image appears 5 seconds later, it is ultimately bound by strict, unforgiving mathematical geometry. You cannot cheat the math.
You really can't. And navigating those mathematical borders can be a nightmare for a casual user. You don't want to spend 10 minutes crafting the perfect prompt and setting up a generation queue only to realize you accidentally plugged an SDXL LoRa into an SD 1.5 based checkpoint.
Which highlights a really elegant solution documented in the ArynCore UI section. To prevent that exact friction, the developers built a feature called dynamic style chips.
It's a brilliant piece of user experience design. When you open the ArynCore Studio and select your base checkpoint from a drop-down menu, the system queries the local database.
Okay.
It checks the architectural metadata of every single LoRa file on your hard drive. It then dynamically populates the UI with only the compatible artifacts.
So if you select an SD 1.5 model, the UI physically hides all your SDXL LoRAs. It prevents you from even making the geometric mistake. It abstracts away all the complex tensor math we just discussed and just lets the creator focus on creating.
Which is how it should be.
And speaking of giving creators a massive playground to operate in, I want to drastically shift gears. Up until now, we have been hyper-focused on visual art drawing, pixels, image generators.
Yeah, that's just the tip of the iceberg.
Right. Looking at the broader ArynCore documentation, the GPU library extends so far beyond images. We're moving into section 6 of the outline here, expanding the sandbox. This software delves deep into audio, video, and workflow automation.
It's a full production suite.
Let's talk about the music studio sidecars. Because as someone who loves music production, the tools they have bundled to run locally are mind-blowing. First up, on port 804, we have the Demix V4 engine running on PyTorch.
Oh, Demix is incredible.
For the uninitiated, Demix is a tool for stem separation. This is the holy grail for remixers and DJs. It is the ability to take a fully mixed, mastered audio file like an MP3 you downloaded and rip it apart into its isolated individual tracks.
Right. And historically, doing this required extremely expensive studio software, or you had to upload copyrighted material to sketchy cloud websites that charged a premium.
Which nobody wants to do.
Running Demix V4 locally on PyTorch puts professional-grade audio extraction directly onto your GPU.
But how does the AI actually do it? Because if I bake a chocolate cake, I can't ask a machine to extract the flour and leave the eggs. The ingredients are chemically bound.
Good analogy.
In an MP3, the frequencies of the kick drum and the bass guitar are occupying the same acoustic space. How does PyTorch pull them apart?
It is a phenomenal application of machine learning. The neural network doesn't listen to the audio the way a human ear does. It converts the audio file into a spectrogram.
A spectrogram.
Yeah, a visual, mathematical representation of frequencies over time. During its training, the Demix model looked at thousands of songs where it had access to both the final mix and the original isolated studio stems.
Oh, I see.
So it learned the distinct visual and mathematical patterns of a snare drum versus a human vocal cord.
So when you feed it a new, fully mixed song, it analyzes the spectrogram, recognizes the shape of a vocal frequency, and uses math to subtract everything else from the picture.
Exactly. And the power ArynCore provides the user here is granularity. You can choose a simple two-stem separation, just ripping the vocals away from the instrumental. You can push it to a standard four-stem separation, vocals, drums, bass, and other. But because they are utilizing the heavy V4 engine locally, you can push it to a highly complex six-stem separation, where the model painstakingly isolates the piano and guitar tracks as completely separate files.
Having that running silently in a background port while you're browsing the web is incredible. But the audio tool that truly sent me down a rabbit hole is running on port 8001.
Let me guess, voice conversion.
Yes, the voice conversion sidecar, utilizing RVC version 3. RVC stands for Retrieval-Based Voice Conversion.
It's a very powerful tool.
Now, I want to be very careful here because people hear the phrase AI voice and immediately make an assumption. They assume it's text-to-speech. They assume you can just type, hello, how are you on a keyboard, hit enter, and the machine will synthesize an audio file of someone speaking. But that is not what RVC is, right?
That is a critical distinction, and the documentation draws a very hard line here. RVC is strictly voice-to-voice conversion.
Meaning you have to provide an actual audio recording as the base.
Yes. You must provide an input file, a recording of yourself speaking a monologue into a microphone, or singing a song.
Okay.
The RVC model does not generate performance. It analyzes the cadence, the emotional pacing, the breath control, and the inflection of your original recording. It then swaps out the timbre, the tonal quality, the resonance of the vocal cords with the target model you loaded.
So if I want an AI voice model to sound angry or sad, I can't just type brackets of angry tone brackets.
Yeah, no.
I have to actually act it out into a microphone. I provide the emotion, the acting, the timing. The AI is simply painting a new vocal texture over my performance.
Exactly. It is an acoustic filter. If you want true text-to-speech driven by a keyboard, ArynCore actually includes that capability in a totally different sidecar running Tortoise TTS, which is a specialized neural text-to-speech engine.
Oh, good to know.
But for musical or highly emotional output, RVC is unparalleled.
And the level of control you have over that RVC engine in the ArynCore UI is what truly defines this local-first philosophy. You aren't just hitting a magic button and hoping for the best. You can manually adjust the pitch shifting prior to the conversion.
Yeah, that's crucial.
For example, say you are a male producer with a deep voice and you recorded a scratch track, but you want to apply a female vocal model to the performance. You can set the pitch shift parameter to +12.
Which mathematically shifts the source audio exactly 1 octave up before it enters the neural network.
Why is that necessary?
Because if you feed a deep bass vocal into a female soprano model without pitch shifting at first, the AI will literally tear itself apart trying to reconcile the frequencies.
It sounds bad.
Oh, it's awful. The output will be distorted, robotic, and full of artifacting. Pre-shifting the pitch ensures the input aligns with the expected frequency range of the target model.
It's all about accommodating the math.
Mm-hmm.
And you can also adjust something called the index rate on a slider from 0 to 1.
Right.
The documentation explains that this tells the machine how heavily it should rely on a supplementary .index file to nail the specific accent and character of the target voice.
It is a balancing act. If you set the index rate to 1, the AI is referencing the target's original dataset heavily, ensuring the accent is perfect. But if your source audio has a lot of background noise, a high index rate will often try to convert that noise into weird vocal chirps.
Oh, weird.
Yeah. Dialing it down to 0.5 reduces the accent accuracy slightly, but provides a much cleaner, smoother audio file. Again, it is about giving the creator the dials to tune the instrument.
It is a staggering amount of power. And they also have an effects rack on port 8002 running a library called Pedal Board, which lets you stack reverbs, compressors, and EQs non-destructively.
Yep.
They integrate video synthesis tools like Sad Talker, which can take a single still photograph and animate it to sync with an audio file, and Animate Diff for full video generation.
The video side is crazy.
It is. But as I was reading through this extensive technical manual, going through API endpoints, PyTorch dependencies, tensor dimensions, I hit a section that completely derailed me.
I think I know what you're going to say.
Because alongside all of this bleeding-edge machine learning infrastructure, ArynCore integrates NAN for dragging and dropping node-based workflow automation. It has a decentralized peer-to-peer chat system utilizing the NKN mesh network, meaning you can message people with 0 central servers and no accounts.
Right.
And then tucked right next to the tensor math is the Witch's Almanac.
Ah, yes, the Witch's Almanac tab.
I literally laughed out loud when I saw this. You are in a fortress of localized AI, monitoring your GPU VRAM, and there is a dedicated section for tracking lunar phases.
It's brilliant.
It pulls daily tarot cards and uses local LLMs to generate personalized interpretations. It calculates astrological charts and allows the user to cast I Ching hexagrams.
It seems like a massive contradiction at first glance. You have the coldest, most rigorous mathematical frameworks, neural networks, vector databases, asynchronous Python routing sitting right next to ancient esotericism.
It does.
But conceptually, it is perhaps the most important part of the entire documentation.
How so?
Because it proves that ArynCore is absolutely not corporate enterprise software.
Yeah.
If a tech giant built an AI hub, it would be completely sanitized.
Right, we were right.
It would track your calendar, your emails, and your Jira tickets to maximize your productivity output for your employer.
Yeah, very true.
The inclusion of the Witch's Almanac proves that this is a highly personalized digital hub built for a multifaceted human being. The philosophy of personal computing has been deeply eroded over the last 20 years. Computers became terminals for corporate services.
Wow.
ArynCore treats the user as a whole person. You might need to track a software bug in the Redmine sidecar at 10 a.m., train an image LoRa at 2 p.m., and consult a human-design body graph compatibility chart at 9 p.m. It embraces the eclectic, weird nature of the individual.
It's a workshop built to reflect the mind of the person sitting at the desk. Which brings us to the final piece of this puzzle.
Okay.
You have this localized fortress. You've created these intricate, highly personal LoRa artifacts. You have isolated your vocal stems and generated video.
Yeah.
What happens to the work? If the entire point is to escape the corporate cloud, how do these creators share their research with the world without becoming the very silos they are rebelling against?
That is addressed in Section 7, Open Source, Archiving, and the Computer's Complement. The Arynwood Technology Organization adheres to a fiercely open-source publication strategy.
Okay, that's good.
They recognize that hoarding this knowledge locally completely defeats the purpose of community evolution.
Right. They don't want to build a new walled garden, even if it's an indie one.
Yeah.
So what is the release mechanism?
Every component we have discussed today, the trained arynwood.safetensors file, the detailed methodology.md outlining the exact training parameters, and the raw source code for the ArynCore UI is published for open public availability.
Amazing.
To ensure the research is treated with academic rigor, they archive the final artifacts on platforms like Zenodo and OpenAir.
What are those?
These aren't just file-sharing sites. They are permanent research repositories heavily utilized by the scientific community. When an artifact is uploaded there, it is minted with a dedicated DOI, a digital object identifier.
Meaning the LoRa file is permanently cryptographically cataloged. It is fully citable in academic papers.
Exactly. And that DOI is explicitly linked to an ORCID profile, which is a persistent digital identifier that distinguishes the individual researcher. It guarantees permanent creator attribution across the entire internet.
And looking at the licensing, all the source code is pushed to GitHub under the Arynwood Technology Organization, released under a Creative Commons 4.0 license, specifically CC BY 4.0. Let's clarify what that actually allows a random person on the internet to do.
CC BY 4.0 is one of the most permissive and collaborative licenses available. It means that anyone, a hobbyist, a student, or even a commercial studio, can download the Arynwood artifact, remix it, adapt it, fine-tune it further, and build upon the work for any purpose, even commercially.
Wow, even for profit.
Yes. The only strict requirement is that they must provide appropriate attribution to the original creator. It is an ecosystem designed to aggressively propel the open source movement forward.
Now, I have to bring up the emotional elephant in the room here. We have spent an hour dissecting the tensor math, the local hardware architecture, the open source licensing.
Right.
But AI art does not exist in a vacuum. It exists in a culture that is currently grappling with deep anxieties about automation.
Very deep anxieties, yeah.
The broader conversation around AI image generation is controversial and, frankly, often deeply hostile. We talked about Lorelei Noble taking hundreds of hours of her own manual, painstaking Procreate brushstrokes and mathematically condensing them into a safe tensors file.
Yeah.
If I put myself in the shoes of a traditional artist, I look at that and I feel a profound sense of melancholy. Isn't it heartbreaking? Isn't it depressing to watch your own hard-fought manual technique, the literal movement of your hand, be automated and replicated by Python code?
It is the defining anxiety of the generative AI era, the fear of replacement, the fear of obsolescence. And it is a completely valid emotional response when you view AI as an external corporate force extracting your labor.
Yeah, some tech giant took my stuff, I'd be furious.
Right. But the synthesis provided at the very end of the Arynwood research paper offers a radically different philosophical framework, because we aren't talking about a corporation scraping the internet. We are talking about a creator utilizing their own hardware to analyze their own art.
That's true.
I want to look very closely at how Lorelei Noble frames this relationship. She argues fundamentally that the AI does not erase the artist. Rather, it acts as a mirror.
A mirror. It reflects, it doesn't replace.
Yes. The generated output of the LoRA, those slightly fuzzy pastel dreamscapes generated on the Dreamshaper checkpoint, are simply the software's unique interpretation of a human's painstakingly developed manual technique.
That's a beautiful way to think about it.
The paper posits this beautiful conceptual equation. Thousands of highly technical developer hours writing the open-source foundational models in UI code, combined with hundreds of deeply personal human brushstroke hours in Procreate, results in a valid current piece of digital art.
It is a collaboration across time and discipline. The developer who wrote the PyTorch routing script in 2023 is unwittingly collaborating with the artist who drew the pastel sketch in 2021. Culminating in a new image generated in 2026.
Exactly. It breaks down the solitary nature of creation. And the quote Lorelei ends her research paper with is something I think every single person grappling with the existential weight of this technology needs to hear.
Lay on me.
Reflecting on the process of seeing her own style mathematically reproduced by her localized GPU, she writes, "This is my computer telling me what it thinks my art represents, and I'll take it as a compliment."
Take it as a compliment. That is stunning.
It completely reframes the dynamic. AI is almost universally viewed right now as a thief, a shortcut, or a sterile replacement for human effort.
Right.
But when you wrest control of it, when you run it locally, off-grid, and train it exclusively on your own blood, sweat, and tears, it becomes a collaborator. It is looking closely at your life's work, finding the mathematical patterns in your specific genius, and reflecting your own intent back at you through a new lens.
It is not a replacement of the human soul. It is a strange, beautiful extension of it into a new medium.
Absolutely.
To look at this incredibly dense, intimidating web of tensors, asynchronous Python scripts, and PyTorch dependencies, and see not a machine trying to render you obsolete, but a mirror actively trying to understand you. That is incredibly powerful.
It changes everything.
We have covered a massive amount of ground today. We started by exploring the fortified bunker of the ArynCore local first philosophy, building an off-grid, asynchronous ecosystem to escape the precarious rental economy of the corporate cloud.
Yep.
We dug deep into the meticulous dataset preparation, the manual tagging, and the exact dials turned the dim of 32, the alpha of 16, the strict limit of 10 epochs to train the Arynwood LoRa without letting it lose its imagination to severe overfitting.
Let's tightrope walk.
Exactly. We explored the breakthrough of cross-checkpoint portability within the SDXL family, alongside the strict geometric mathematical barrier that prevents those modern tensors from mapping onto legacy SD 1.5 models.
Right, the origami problem.
And we unpacked a wildly eclectic local sandbox from isolating piano stems with Demix V4 to pitch-shifting human emotion into new vocal timbres with RVC, all sitting right next to an AI-powered tarot reader, anchored by a fiercely open-source CC BY 4.0 ethos.
The documentation and the research combined represent a massive paradigm shift in how we think about computing and creativity. We are watching the leading edge of a movement away from renting generic, sanitized, heavily restricted cloud models.
Yeah.
It is a pivot toward owning highly personal, hyper-specific, beautifully messy tools on our own physical hardware.
And it leaves me with one final, slightly provocative thought for you to mull over as you go about your day.
Let's hear it.
If our tools, our digital paintbrushes, our audio stem extractors, our localized voice models, if they can now mathematically learn, adapt to, and actively mirror our past creative decisions, does the act of creation in the near future fundamentally change? Does it become less about the physical, manual stroke of a pen on a tablet and more about curating, directing, and having a continuous evolving conversation with our own digital ghosts?
It is a fascinating frontier. The tool is no longer a static piece of wood and horsehair. It is alive with your own history.
And those muddy waters between the artist, the medium, and the machine, I think that's exactly where the most beautiful new art is going to grow.
Well said.
Thank you so much for joining us on this deep dive. Keep experimenting, keep owning your tools, and we'll see you next time.